Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Aerodynamic Performance of CO Flow Jet at Different Angle of Attacks Dr. Asad Ahamed. R*1, Dhuruva. P number 1, Agadheesh. S number 2, Lakshman Ragavendar. N number 3, Jim Ebenezar Manickam. M number 4 *1 Assistant Professor, Sister Scale, number 1, number 2, number 3, number 4 UG Student, *1, number 1, number 2, number 3, number 4 Department of Aeronautical and Aerospace Engineering, KCG College of Technology, Karapaksam. Abstract, the active flow control over aerofoil using CO flow jet, CFJ. With injection and suction slot on upper surface in leading edge, LE, and trailing edge, TE, of the aerofoil. To achieve high efficiency, the CO flow jet is analyzed with different angle of attack. The NACA 4412 aerofoil is used for both baseline and CO flow jet, where the CFJ can be worked with any aerofoil one. The high angle of attack is achiever at lower speed without stalling. The Ansys CFD software is used with the two-equation turbulence. The overall performance is increased by 33% to 66% compared to baseline airfoil. Fig.2, baseline keywords aerofoil, angle of attack, Ansys CFD, CO flow jet, CFJ, LE, and TE. Introduction. In order to achieve high performance, the active flow control method is used. Where the CO flow jet, CFJ, with injection slot and suction slot at leading edge, LE, and trailing edge, TE, as a reference, the CFJ aerofoil is compared with a baseline aerofoil series NACA 4412. Where the aerofoil is designed with CFJ's injection and suction slot. The chord length is 0.151 m. The CFJ aerofoil is modified design of baseline aerofoil by translating the modified surface lowered vertically 1.67% plus or minus 0.05% of chord 2. The injection is located at 6.72% plus or minus 0.05% and suction slot is located at 88.72% plus or minus 0.05% of the chord from the LE. The area of injection slot is 1.50% plus or minus 0.05% and suction slot is 1.60% plus or minus 0.05% of the chord. Where here we use the slot area as same 1.56% of chord which is 0.00236 m. Geometry setup. The CFD software is used to simulate and study the flow over the aerofoil. The K turbulence, 2 equation, module is used as wall function to save CPU time. The turbulence equation is same through all the condition. In order to reduce the time taken by the computer, 2 turbulence equation is used. 3. The Reynolds number taken here is 50,000 which is lowest number for the aerofoil NACA 4412 as per the database which is 50 m/s. Where the aim is to achieve higher angle of attack with minimum speed, where Re is the Reynolds number, a dimensionless number used in fluid mechanics to indicate whether fluid flow past a body or in a duct is steady or turbulent. 4. Fig.1, CO flow jet. Fig.3 IJERT 10 is 060422 www.ijert.org 898. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. Considering the pressure, velocity, area, and mass flow rate at the injection and suction slot of CFJ, the C coefficient of jet, C, varies with respect to AOC coefficient of CFJ. MJ mass flow rate of CFJ, density of air. U velocity of free stream S area, where C varies with AOA. The value of C varies from 0.08 to 0.25 with respective to AOA of the airfoil. At Mach 0.145, C equals 0.08 at 0 degrees, which is more efficient in comparison. The C is estimated by comparison of value at every condition. 5. Fig.5, B velocity contour at AOA 0 degrees. The Fig. 5, A, b, shows the pressure and velocity contour respectively. The operating condition is Mach number 0.145, which is the minimum velocity of the airfoil as per the database. The velocity is same as all the angle of attack. Where the force generated is we found through the journal paper we gone through. There is force produced on aerofoil due CO flow jet in both X and Y axis. Fig.4, AOAV/SC results F momentum force mj mass flow Vj velocity at slot Pj pressure at slot Aj area at the slot, angle between slot to perpendicular to chord. Fig.5, A pressure contour at AOA 0 degrees. Fig.6, A. IJERT 10 is 060422 www.ijert.org 899. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. Fig.7, b, Fig.6, b, the lift coefficient with respective to AOA, where in the baseline aerofoil the CL stops to drop gradually beyond 15 degrees, where in CFJ aerofoil the CL values stay high at AOA of 30 degrees. The drag coefficient with respective to AOA, where the CD at 0 degrees and 5 degrees are in negative because due to the CFJ there is a momentum produced in the aerofoil which is in X direction. After 50 degrees it starts to drop in larger amount which is greater than the drag produced beyond that angle. In accordance with the journal paper, the flow separation haven't take place up to AOA of 20 degrees, so we go beyond the AOA of 20 degrees to check the flow separation taken place in comparison of baseline aerofoil. The CL range from 0.356 to 1.0076, where in CFL the CL range from 0.374 to 1.105, which is comparatively higher. The drag coefficient is range from 0.0204 to 0.401. At 20 degrees, and in CFJ due to the momentum force negative drag formation take place where 0.03314 to 0.20877, at 20 degrees, which is much more lower than the baseline aerofoil, and the drag produced by the baseline aerofoil at 20 degrees is produced CO flow jet at 30 degrees 6. Where the significant increase in efficiency at m equals 0.4, but here the efficient value of CO flow jet is found at lower velocity m equals 0.145 for higher angle of attack. In Fig.7, A, shows the streamline of the flow from injection slot to suction slot where the flow is attached to the surface of the aerofoil, but in the Fig.7, B, the flow separates and not attached to the surface of the airfoil, which results in larger amount of increase in drag and massive drop in lift beyond that AOA 8. Conclusion: the CO flow jet aerofoil design in this report is capable to reduce drag force and convert streamline vortices to additional thrust, which is much more effective up to AOA of 45 degrees and at lower velocity m equals 0.145. The obtained results from the analysis proves that the CFJ airfoil will produce more lift coefficient than the baseline airfoil. This is because the downstream gets energized due to the injection air, so that the airflow remains attached over to the body, and it increases the lift coefficient 9. Where there is no change in flow separation beyond the AOA OD 50 degrees, even though coefficient of CFJ is tested with higher value up to C equals 0.5, the flow separation remains constant. Acknowledgements: we thank our management and our principal Dr. P. Devasundari for the opportunities given to us for our career development. We feel indebted to the head of the department, Dr. K. Vijayaraja, Department of Aeronautical and Aerospace Engineering, KCG College of Technology, for all his encouragement, which has sustained our labor and efforts. We express our deepest gratitude to the internal guide Dr. Asad, Ahamed, Assistant Professor, Department of Aeronautical Engineering, KCG College of Technology, for his valuable guidance, ideas, and support. Fig.7, A. We would like to thank all other faculty members of our department for their help and advice throughout our life in this campus. Finally, we are thankful to all our friends and all others who encouraged us and helped us in doing this project. IJERT 10 is 060422 www.ijert.org 900. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 References 1 Novel Flow Control Method for Airfoil Performance Enhancement using CO Flow Jet G. E. Cheng Jia and Craig D. Paxton, University of Miami, Coral Gables, Florida. 2 Jet Effects on CoFlow Jet Airfoil Performance G. E. Cheng Jia S. Wei Gao, and Craig D. Paxton, University of Miami, Coral Gables, Florida, 33124 Paper 1222-1230. 3 Numerical Investigations of Injection Slot Size Effect on the Performance of CO Flow Jet Airfoil Baiyuan Wang, Bahadao Kasauni, Jonathan Levy, G. E. Cheng Jia Department of Mechanical and Aerospace Engineering University of Miami, Coral Gables, Florida, 33124. 4 Experimental Investigation of Jet Mixing of a CO Flow Jet Airfoil BPE Dano, D. Kirk and G. C. Jia Department of Mechanical and Aerospace Engineering University of Miami, Coral Gables, Florida, 33124. 5 Wind Tunnel Testing of NACA 0021 Aerofoil with CO Flow Jet Emilansan RAJAN 1, T. S. Gauthaman 2, C. Ganesan 3, K. Balaji 4, K. M. Kiran Babu, Depart 79 Ment of Aeronautical Engineering Karpagam Institute of Technology, Coimbatore, Tamil Nadu, India IXCET 2015. 6 G. E. Cheng Jia, G. C., and Paxton, D. C., present a novel flow control method for airfoil performance enhancement using CO Flow Jet, Applications of Circulation Control Technologies, edited by Jocelyn, R. D. and Jones, G. S., Progress in Astronautics and Aeronautics, Volume 214, AIAA, Reston, VA, 2006, pages 293314, Chap.10. 7 Aerodynamic Performance Enhancement for Flapping Airfoils by CoFlow Jet Tao Wei, Baifeng Song, Wenping Song, Wenqing Yang A Zonghua School of Aeronautics, Northwestern Polytechnical University, XI number and 710072, China B. Yangtze River Delta Research Institute, Northwestern Polytechnical University, Taikang 215400, China. 8 Performance and Energy Expenditure of CoFlow Jet Airfoil with Variation of Mach Number A. Lefebvre B. Dano, W. B. Bardo, M. D. Franzo, and G. C. Jia University of Miami, Coral Gables, Florida, 33124. doi 10.2514/1.C033113. 9 Application of CO Flow Jet Concept to Aircraft Lift Increase I Likithas Siddhanath Application of CO Flow Jet Concept to Aircraft Lift Increase IJERT 10 is 060422 www.ijert.org 901. This work is licensed under a Creative Commons Attribution 4.0 International License.